Okay, guys, welcome. Today we're going to talk about different ways that we can characterize data. Okay, now frequency graphs and tables show us how data are distributed over various categories, and we can more formally say that these give us a distribution of a data set. Now, the distribution of a variable or data set talks about the way that its values are spread over all possible values. And we can easily show a distribution visually with a table or a graph. And a lot of times we'll do this with a graph. Now, first, we need to talk about ways to measure the average, right? And of course, there's three different interpretations of the word average. So of course, we have the mean, the median, and the mode. Now, the mean is what you usually think of when you think of average. It's like your arithmetic average. That's where you add the total number of the data points and you divide by the number of data points, right? Then you have the median, which is the middle value. And of course, those you would arrange from least to greatest, and then you would eliminate the lowest and the highest values until you're left with either one or two numbers. If you're left with one number, that's the median. If you're left with two numbers, then you would find the mean of those remaining two numbers. And then, of course, the mode is the number that occurs most frequently in the distribution. You could have no mode. You could have more than one mode as well. So just keep that in mind. So in this first example, we have 8 grocery stores sell the PR Energy Bar for the following prices. We want to find the mean, the median, and the mode for these prices. Well, for the mean, we're going to add 109 plus 129 plus 129 plus 135 plus 139 plus 149 plus 159 plus 179, and we'll divide that by 8. So if we grab our calculator and we punch this in, so 109, 129, 129 again. So that should be a flag going off about one of our other averages, but we'll get to that. Plus 139, 149, 159, and 179. So if we add all them together, and it looks like I missed a decimal here because I'm getting 129, which is not right. Okay, let's try this again. Okay, I think that's better. So when we add all these, we get $11.28. And of course, I want to divide that by 8. And it looks like we get that the mean of this data set is $1.41. Okay, now we can find the median. Now again, how do we find the median? Well, we line them all up from least to greatest, and then we cross off low and high. Now in this data set, they've already arranged it from least to greatest for us. So we can start crossing low, high, low, high, low, high. And we see that we have 2 left, right? So now we just take the average of those 2, the mean of those 2. And if we do that, we would get 137. Okay, and then last but not least, we can talk about the mode. And of course, we only have one number that repeats itself, and that's 129. So that's the mean, median, and mode for these 8 prices. Okay. Now next, we'll talk about the effects of outliers. Now an outlier in a data set is a value that's much higher or much lower than almost all the other values. Now an outlier can change the mean of a data set but does not affect the median or the mode, right? So for example, say that one player on a college basketball team is offered an NBA contract. Is it fair to conclude that the player's offer is the mean contract offers from the NBA teams for the entire team? And of course, this is no, because everybody else would be 0, right? Most of the others are 0. right? So that MBA contract would be an outlier, right? Now, how does an outlier affect the three different average types? Well, we just talked about that the mean, it'll affect the mean, but of course not the median or the mode. And we're going to do an example of that. Now, a track coach wants to determine appropriate heart rate for athletes during their workouts. She chooses 5 of her best runners and asks them to wear heart rate monitors during a workout. In the middle of the workout, she reads the following rates for 5 athletes. So we have 130, 135, 140, 145, and then 325. Now, if you know anything about heart rates during exercise, this is not good, right? This would be, right? That would be, you'd be dead, right? So, of course, there's something wrong with that heart rate monitor, and that's producing an outlier in this, this data set. Now, if we use the mean as the measure of average, and you'd have to add all these, we'd have to add 130, 135, 140, 145, and 325, and divide that by 5, what would we get? Well, 130 plus 135 plus 140 plus 145 plus 325 would give us 875 divided by 5, and that would give us a 175. Right? Now, this is much higher than the 4 other athletes, but of course much lower than the 325. But if you were to calculate the median, you're going to get cross off low and high, and you would get that the median is 140, right? And it turns out that this is the better average here. And that's because this is affected by the outlier, whereas this is not. Right, so that's something to keep in mind about outliers. Okay, now, because there are 3 different ways to interpret the word average, this can sometimes lead to confusion, right? So you might not be told enough about what type of average to use, or you're not given enough information of how the average was found. And we're going to look at an example of how that can create confusion. Now, newspaper survey wages for assembly hours in regional high-tech companies and reports an average of $22 per hour. Then the workers at one large firm immediately request a pay raise, claiming that they work as hard as employees at other companies, but their average wage is only $19. Now, management rejects the request, telling them that they are actually overpaid because their average wage is in fact $23. And of course, can both sides be right? Explain. And the idea here, of course, is that yes, both sides can be right. Because they probably use different types of averages. So for example, management, if they reported $23 an hour, they might be using the mean as their measure of average, and the CEO's salary is throwing everything off, right? And of course, the $19 an hour employees might be using the mode or something like that. So that's the idea. Now, this is an interesting problem. So we have that all 100 first-year students at a small college take 3 courses in the course studies program. The first 2 courses are taught in large lectures with all 100 students in a single class, and the third course is taught in 10 classes of 10 students each. Now, students and administrators get into an argument about whether classes are too large. The students claim that the mean size of their core studies classes is 70, where the administrators claim that the mean class size is only 25. Can both students be right? Explain. Now, both sides are right here. And it's all about perspective in this example. Right? So if you're a student you have 3 classes. Now, in your first 2 classes, you have 100 students. And in your third class, you have 10 students. Now, if you look at, now again, here they're saying mean, so we don't have the way out of saying that they use different types of averages. If we take the mean of this, we're taking 210 divided by 3, and that's where the 70 comes from. Now, if you're an administrator, you don't see it this way. Because, yeah, class 1 and class 2 have all 100 students in a class, but there are 10 class 3s with 10 each. Right? So now when you find this average, you're taking 100 plus 100 plus 10 times 100, so you're going to get 300. And then this is going to be divided by, well, you have 10 class 3s plus class 1 and class 2, so divided by 12. And then, of course, if you take this average, you're going to get 25. Right? So in this problem, it's all about perspective. So there's ways that sort of many different angles can be taken to make these averages different. Okay, so now we've talked enough about averages, we can now talk about the shapes of distributions. Okay, so there are 3 characteristics that we pay attention to. So we have the number of modes, the symmetry or skewness, and the variation. We're going to talk about all 3 of these. Okay, now first we'll talk about with a number of modes. Now, if we look at some figures, I basically just drew some instead of getting them out of the book, we can see how a smooth curve can be fit to a distribution. Right? Now, one way that you can characterize a distribution is by the number of peaks. And I should put, like, for example, you could have like bars that are representing the general trend of this data, and that would be an example of fitting this data to it. All right, so something like that. But anyway, we can characterize a distribution by the number of modes or the number of peaks that it has. Right? So if a graph has 1 peak, we say that it's unimodal. If a graph has 2 peaks, and they don't have to be the same height, one could be higher than the other, we call that bimodal. Right? If your distribution has no mode, we say that that is a uniform distribution. And there may be other distributions, of course, that have more than 2 modes, and we would just say that it has however many modes that it has. Okay, so in this next example, we're going to talk about how many peaks would you expect for each of the following distributions. We'll talk about why, and we'll make a rough sketch for each distribution. Now for part A, we have the heights of 1,000 randomly selected women. Okay, so if you have 1,000 randomly selected women, you're going to have, most people are going to sort of hover around the average. And then you'll have some that are exceptions to the rule, some being very tall and some being very short. So this we would probably expect 1 peak. Right, and of course we would say that this is the average height on this axis, not the average height, but the height. And this would be the number of women. So most we would expect to be centered around this average. Now in part B, we have hours spent watching football on TV in January for 1,000 randomly selected adult Americans. Okay, now this one you could have a couple of different peaks, right? Because of the following. Now you're going to have some, so the number of hours will be here, And of course, number of people here. Now, you could have several peaks because, of course, you're going to have a lot of people that don't watch football. But then you're going to have people that do watch football, but they only want to watch their home team's game. And then you have the group that wants to watch football all day long, which is the group that I belong to. But anyway, this would give you an example of a distribution with several peaks because you have different levels of people being interested in watching football. Okay. Part C, we have the weekly sales throughout the year at a retail clothing store for children. So weekly sales. And number of times. Right. So for weekly sales throughout the year at a retail clothing store for children, I should say that this is the month, and this is the sales. Now, there's usually two main times that you have children getting new clothes, right? And of course, the one time is back to school, and the other time is before summer, right? And then other than that, it stays pretty consistent for the year, right? So this would be what we would call a bimodal distribution, just based on those two things there. Okay, and then finally for part D, we have the number of people with particular last digits 0 through 9 in their social security numbers. So now, of course, this is the oddball case because here you would have the digit and here you have the number of people. And social security numbers are designed so you can't, there's no predictability in the number, right? So you would have the fact that there is no digit that occurs more times than the other. So this would be an example of a uniform distribution. So those are some examples of some of these distributions. Now, the next type of measure that we'll look for on a graph is whether it's symmetric or if it's skew. So what you can look at is sort of how close one half of the graph is to the other half. So we say that a distribution is symmetric if its left half is a mirror image of the right half, right? So for example, I forgot to include, when I was preparing this, I forgot to include a symmetric one. So a symmetric distribution would look something like this, right? And the idea would be that you have the same thing on each side of the middle of the graph. Now, when a distribution is not symmetric, there must be values that are more spread out on one side than the other, right? And that's when we call the distribution skewed. When the values are more spread out on the left, meaning that some values are outliers at low values, we say the distribution is left skewed because it looks like a tail has been pulled toward the left. And then when the opposite occurs, you say that it's right skewed. So this would be an example of left skewed and right skewed, right? So the direction is where, right, you sort of have the longer tail, right? So left skewed, you see the tail on the left, right skewed, you see the tail on the right, right? Or you could think of it also as the opposite of where the peak is, right? So now what happens to your measures of your averages? Well, if a graph is left skewed, it will pull the mean and the median to the left of the mode, right? So if you go from left to right, you'd have the mean, then the median, and then the mode on a left skewed graph. So it would look something like this. So you'd have mean maybe somewhere here, median here, and then the mode is always at the peak. Now on the right skewed, it pulls the mean and the median to the right of the mode. So from left to right, you'd have mode, median, and mean, right? So you'd have the mode would be here at the peak, then the median, and then the mean. Now in the symmetric case, they're all equal, and it's just wherever the peak is. So this would be where the mean, median, and mode all are. So those are different effects of having a symmetric graph or left or right skewed graph. Okay, now for each of the following situations, we'll talk about whether we expect the distribution to be symmetric, left skewed, or right skewed. Now, of course, for the heights example, we have heights of a sample of 100 women. We would assume that that would most likely be symmetric. Right, because since we're just comparing women to other women, we would expect that most would be clustered around the average, and then there are some outliers, but probably equally so on both sides. Now for part B, the number of books read during the school by fifth graders. We would probably say is left skewed. Right, and the reason why is because we would probably have our peak towards the end of the year when the reading skills are better, right? So we would say that this type of data distribution would be left skewed. Now in part C, we have the speeds of cars on a road where a patrol car is using radar to detect speeders. So if you've ever driven before and you see a cop, what of course do? You slow down even if you're not going above the speed limit because you're paranoid. So you have that you're going to have most people would be going slow. And then you'd have some of the daredevils that either don't see the cop or don't care that there's a cop there. Would continue to go fast. But this, of course, would mean that you have a right skewed distribution. Right. So those are different sort of scenarios where you could have different types of symmetry or skewedness. Now, the last type of way that we'll talk about characterizing data in this video is to look at its variation. And of course, the variation just describes how widely the data values are spread out around the center of a distribution. So as a couple of examples, in this first graph, you have that everything is pretty close and clustered to the middle. So this would be low variation. Then in the next one, it's a little bit more spread out. So we might say that this is moderate variation. And then in the last one, it's very spread out. That peak is very wide. So we'd say that this is high variation. So those are different ideas of variation. Now, I think a good example to see this is how would you expect the symmetry and variation to differ between the times in the Olympic marathon and times in the New York marathon? And in the New York marathon, remember that anyone can go. So if we were to draw this out, we would have most people would center around the average, right? And there'd be a lot of variation. Let me draw this a little better. Because you're going to have most people that are a general fitness level in this, but then you have some that are the world-class athletes that would be up here, and then you have some people that probably realized into mile one that running a marathon was not a good idea, right? So here you would expect probably a symmetric distribution with high variation. Now for the Olympic marathon, the difference here is that the best of the best go. right? You have to win a qualifying match, and you have to train for years and years and years to get invited to the Olympics, right? So what you would probably expect here is low variation, and all the times would be probably pretty close together. It would probably be seconds separating these athletes, right? So we would probably expect a left skewed distribution with low variation. So that's some sort of application of using variation. So that concludes this video on how to characterize data. I hope you enjoyed, and I will see you next time.